Question 4, this is where we are going to make a beam where we're going to put a hinge point at the quarter span position to see whether it is the equivalent to a continuous beam. We split the beam into two spans, one with an overhanging cantilever, it's with a back span, and the other one is a simple support effectively. Spans are 10 meters, the loading's 10 kilonewtons per meter, and the beam is a UK section, which is a 533, and the I value and the E value given. E for steel, which is the modulus, and we can go through all of the methods that we use in this example with the hints given to figure 2.4.1, 2.4.7 and so on. Question 4a, and we are going to set the beam up and split the spans, so we show 0.25 L where the hinge is, 10 meters, 2.5 meters and 7.5 meters, and it's 10 kilonewtons a meter, and we know that there's zero moment in the hinge point, so if we split the spans then we put equilibrating or balancing forces in place, and we call them span A and span B. So the reaction, the balancing force, is given by taking the reaction from the right hand side span B, which is 10 times 7.5 over 2, 27.5, and the bending moment in that span, which is hopefully the same on both sides, is WL squared over 8, 10 times 7.5 squared over 8, which is 70.3 kilonewton meters. And we're going to now give the moment at the support, which is given by 37.5 times 2.5 plus 10 times 2.5 squared over 2. That's shown in the equation, and it gives 125 kilonewton meters. Question 4a continued, and this is where we're going to find the central reaction, and we just need to set up the beam on the left hand side, and we just remember that this is a balancing force we put in, and we're going to take moments about a point A to find the reaction R. So we set up the forces again, 2.5, 10 kilonewtons per meter, moments about A, R times 10 gives 10 times 12.5 squared over 2 plus 37.5 times 12.5. We run through the figures, and this gives us 125 kilonewtons for the reaction. Question 4b, and again we set this up, we set up the two sets of spans and the deflection at the tip of the cantilever, and we're going to add this to the mid-span deflection by the law of superposition. So we use figure 2.3.7. First of all, we assume it's a pure cantilever because we know that equation, WL to the 4 over 80I, and we put in the figures, and the pure cantilever deflection would be 0.35 millimeters. And then if we go to figure 2.3.2, we know that it goes upwards from that figure, and the tip deflection is prorated 15 divided by 4 times 0.35 in an upwards direction gives 5.25 millimeters. And in the second part, 4b, we're going to work out the tip deflection from the equilibrating force, which we're going to need, and this was 37.5 kilonewtons, back to 4a, and we assume, again we're going to do a similar method to the previous example. We're going to take a pure cantilever deflection, which is PL cubed over 3EI, putting in the values gives us 1.4 millimeters, and we go to figure 2.3.5, and the tip deflection is 14 compared with what it would be as a value of 3. This is simply numerical value, so if we prorata 14 over 3 times 1.4 gives us 6.5 millimeters deflection downwards. And finally, mid-span, span B is the other deflection, 5WL to the 4 over 384 EI will give us 3 millimeters. So the total, we've got to add those three components, so from 4B before minus 5.25 plus 6.5 plus 3 gives you a total of 4.25 millimeters, which is essentially the mid-span deflection. Question 4C, and we recap. It's 125 kilonewton meters. This is the bending moment in the middle, 70 kilonewton meters, and we had 4.25 millimeters. That's from 4A and 4B. If we go to reference figure 2.4.1 for a 2-span continuous beam, the bending moment's given 0.56 WL squared over 8. The support moment is WL squared over 8, which is 125 kilonewton meters. The mid-span moment 0.56 WL squared over 8, which gives 70 kilonewton meters. This is the same on both sides. And the deflection is 0.4 times the equivalent simply supported beam deflection, 5WL to the 4 over 384 EI, and it gives you 3.8 millimeters. So we can see that the two beams give the same result if we allow for a 10% error margin in the deflections. So the two beams are equivalent. Thank you for listening.